Hi everybody. So today's lesson is an introduction to waves. So we have finished mechanics, which is worth 6 credits, and external standard, and we're starting this new standard, waves, which is worth 4 credits. It's a relatively shorter topic and it's quite an easy one, and it's divided into 3 parts, but there's only one booklet. So the first part we're going to look at is about interference. The second part is about standing waves, and the third part is about Doppler effect. So I'm starting with what you know first. And today's lesson is mostly a recap of what you did in year 12. Okay, so it's merely an introduction, and I'll photograph my notes and I'll put that up as well. So, in order to understand what a wave is, we need to know what a pulse is. So a single disturbance in a medium is called a pulse, and that's how you represent a pulse, and that's the direction in which it's traveling. So what's the difference between a pulse and a wave? A wave is a succession of pulses. So if you have a rope and you keep moving your hand up and down, you have a succession of pulses, and that generates a wave. Okay, so what is the function of a wave? So what a wave does is that it transmits energy. It carries energy from one place to another. That's what a traveling wave does. And the thing is, the material medium does not get transferred from one end to the other. What you do have, of course, is local disturbance. Okay. Now, all waves are classified into two. There's what's called mechanical waves. Now, mechanical waves are waves like sound waves, waves on water, waves on a string or a slinky. Now, these waves are called mechanical waves because they need a medium to travel through. Another word to travel through is called propagate. Okay, so it needs a medium for propagation. And these mechanical waves can either be transverse or they could be longitudinal waves. The other type of wave is what we call electromagnetic waves. And electromagnetic waves are waves that form the electromagnetic spectrum. So you have your radio waves, you have your visible light, you have the infrared and the ultraviolet, the X-rays, the gamma rays, okay, the radio waves, microwaves. So they're all electromagnetic waves. Now, electromagnetic waves are mostly, they're all transverse waves, and they all travel with the same speed in a vacuum, which is the speed of light, which is 3 times 10 to the power of 8 meters per second. Okay. Now, electromagnetic waves are related to each other by the wave equation, V equals F lambda. So the difference between one electromagnetic wave and another is that they all have different frequencies and therefore different wavelengths. However, the product of frequency times the wavelength will always give you 3 times 10 to the power of 8, which is the speed of the wave in a vacuum. Now, depending on how the particles of the medium vibrate, you've got your transverse wave and you have your longitudinal wave. So in a transverse wave, and that's how you represent a transverse wave, in a transverse wave, the particles move up and down while the wave moves forward. So the particles actually vibrate perpendicular to the direction in which the waves move. Now, transverse wave consists of crests or troughs, and the distance from one crest to another is a wavelength, or the distance from one trough to another is the wavelength. Okay. A longitudinal wave, on the other hand, are waves like sound waves, and over here the particles of the medium move back and forth, and that means the particles of the medium vibrate parallel to the direction in which the wave moves. And a longitudinal wave consists of compression, so where the particles all get close together, or rarefactions, where the particles are spread out. Okay? Just moving on. Now we're looking at some of the terms that's used in waves. So these are some of the terms. So one of the terms that we need to know about is the word phase. You've just come across this word phase in simple harmonic motion, so it won't be that foreign or new to you. So the word phase indicates the position and the direction of motion of a particle, exactly the same way as we defined phase in simple harmonic motion. Okay, now the reason why we have the word phase is because its definition, its term is used in the definition for wavelength. So what is a wavelength? A wavelength is the distance between two consecutive particles that are in phase. So two particles on the crest of the wave, they're all in phase, but consecutively, if it's one crest to the other, or from one trough to the other, or from one of the ones in equilibrium to the one in equilibrium there. Okay, so that's your wavelength. Amplitude is maximum displacement. So the amplitude, just like we did in simple harmonic motion, it's always from equilibrium to the greatest displacement. So from equilibrium to the crest, trough, or from equilibrium to the crest. So it could be either. Amplitude is also represented by capital A. Okay, that's a symbol for wavelength. It's called lambda. It's a Greek letter. Then you have the word frequency. So we've come across frequency in SHM as well. So frequency is the number of complete waves that pass a point in 1 second. It has two units. It is hertz or per second. It can be either. Okay. Period is how long it takes a complete wave to pass a point, and that's measured in seconds. Okay, and a complete wave consists of a crest and a trough. So one complete wave is from there to there. Okay. Then the connection between period and frequency, F is 1 over T, or T is 1 over F. All right. Okay, so those are the terms that's used in waves. Now just talk a little bit about sound waves. So sound waves are mechanical waves. So and they are longitudinal waves. Now the way the sound energy is passed through a medium is because of the vibrations of the particles, the back and forth vibration. So energy is transmitted from one particle to the next. So if you're looking at the speed of sound waves, it depends how closely the particles are arranged. So in a gas, where the particles are further apart, it's going to take longer for the energy to be transmitted from one layer to the other. Okay, so usually the speed of sound in air is about 330 meters per second. It could vary depending on if the air is hot or cold, if it is damp air or dry air, if it is, if it's the air above the sea may have moisture and salt particles. Okay, so it varies. Sound waves through a liquid will travel faster than sound waves through a gas because the particles of a liquid are closer together. So in water, it's about 1,500 meters per second as opposed to 330 meters per second in air. And sound waves travel fastest through solids because the particles are closely packed in solids. So that's just a little bit about sound waves. Okay, so the next thing we are coming to is the bending of waves, which is diffraction. Okay, so we learned about this last year, and just to explain this, if you're standing outside a room where there are people and the people are talking, you may not be able to see them, but you can hear them. And the reason why you can't see them is because, yes, light also travels as waves, but its wavelength is really small. So it's hard for light to bend a lot around corners. That's why you can't see them. However, sound waves have a much longer wavelength and they can bend around corners. So diffraction has to do with the bending of waves around corners. There is no change in medium, so there will be no change in speed, there will be no change in frequency, and there will be no change in wavelength for diffraction. Now these two diagrams here, the first two, this one, these blue lines are what we call wave fronts, and these are parallel wave fronts, and they represent the crests of waves. The red line, the arrow, is the ray, or it's the direction in which the waves are moving. So if there's a partial barrier, the waves can't go through the barrier, but they can bend around the barrier a little bit if the wavelength is small. However, if the wavelength is big, the wavelength is from one blue line to the other. Okay, so the gap here is bigger compared to that one. So the waves can bend more, okay, because the wavelength's bigger. And the last one is, you'll remember this, if your incoming wavelength is similar to the size of the gap, then what you get is semicircular wavefronts. Okay, so you get semicircular waves when the size of the gap matches the wavelength of the waves. All right, okay, so that's diffraction. Now, the other thing that we have to remember is about interference, and this main thing of the first part of waves is all about interference. So I'm just going to talk to you a little bit about what interference is. The word interference means come in between. Like when you're talking to someone and a third person talks, you probably say, don't interfere. Okay, similarly, you have the word interference to indicate two waves traveling in opposite direction. It doesn't have to be two, it can be any number. Waves traveling in opposite direction, when they go through each other, they interfere with each other. Okay, and if the waves have got the same speed and the same wavelength and the same frequency, then this interference will produce what we call interference patterns. Okay, and these interference patterns depends on how the waves combine to form the resultant wave. Okay, now in order to get that resultant wave, it's waves coming from different sources. So that brings us to the term path difference. So path difference, or PD, is the difference in distance traveled by the waves to reach a particular point. We'll come back to this more later, more in the next lesson, but path difference is an important thing that you need to know in year 13. Okay? Now, also, this interference can be constructive or it could be destructive. So the word constructive is building up. So when do you get constructive interference? Constructive interference happens when the waves interfere in phase. Okay, that means where a crest combines with a crest or a trough combines with a trough. So what happens is they build each other up, and the building each other up results in high amplitude waves. Okay, and this happens when the path difference, the difference in distance traveled by the waves is a whole number of wavelengths. So path difference is measured in terms of wavelengths. Okay, N stands for the order number, and we'll talk more about that in tomorrow's lesson. But you might recall that constructive interference results in what we call antinodal lines. So antinodes are areas of constructive interference, and if the waves are two-dimensional, then you have antinodal lines. Okay, all right. Then the next one is destructive interference. Destructive interference is when the waves have a cancelling effect. And when do waves have a cancelling effect? This happens when a crest combines with a trough. Okay, and you get areas of calm if it's water, and if it is sound, it'll be areas of quiet, and if it's light, you will have dark regions. Okay, destructive interference produces nodal lines. Okay, and the path difference for your destructive interference is that the formula is n minus half lambda. Okay, so it's half a wavelength apart. All right, odd multiples of half wavelength actually. All right, then I've talked about interference of sound, I've talked about interference of light, and I think that is all for today's lesson, and I hope that made sense. Now at the end of this video, it's a slightly long one, sorry, there are some questions on interference pattern. Could you please do that? And I will post the answers up for that as well. So bye for now.